So here's something I want you to think about as you settle in tonight. Right now, wherever you are, there's about 10 trillion tons of air sitting above you. 10 trillion. That's the weight of the atmosphere pressing down on every square inch of the Earth's surface. And somehow, you don't feel it. You're lying there, comfortable, breathing easily, and this enormous ocean of gas is just doing its thing overhead, swirling, shifting, heating up, cooling down, carrying moisture halfway around the planet and dropping it exactly where you didn't expect. That's weather. That's the thing we complain about at bus stops and plan weddings around and check on our phones 6 times a day. And honestly, the deeper you go into understanding how it actually works, the more astonishing it becomes that any of it works at all. Let's start somewhere simple. Let's start with the sun. Everything, and I mean everything, about weather begins with the sun. Without it, Earth would be a frozen rock drifting through space at about minus 270 degrees Celsius, give or take. No wind, no rain, no clouds, no storms, just silence and ice. But we've got this star, about 93 million miles away, pouring energy toward us at a rate that's almost hard to comprehend. Every second, the sun releases roughly 3.8 times 10 to the 26th power watts of energy. That's a number so large it stops meaning anything, so let me put it differently. The amount of solar energy that hits Earth's atmosphere in 1 hour is roughly equal to the total energy that all of human civilization uses in an entire year. 1 hour. And most of that energy just bounces back into space or gets absorbed by the oceans. The tiny fraction that sticks around and does work in our atmosphere, that's what creates every breeze, every thunderstorm, every hurricane, every gentle spring rain you've ever walked through. Now, here's the thing that makes weather possible instead of just making everything uniformly warm. The sun doesn't heat the Earth evenly. And this is so fundamental, so absolutely central to everything we're going to talk about tonight, that it's worth really sitting with for a moment. If the sun heated every part of the Earth exactly the same amount, there would be no weather. None. The atmosphere would just sit there, perfectly still, like water in a bathtub that nobody's disturbed. But the Earth is a sphere, and it's tilted on its axis by about 23.5 degrees, and it's spinning, and different parts of its surface are made of different stuff: ocean, desert, forest, ice. And all of those things mean that solar energy arrives unevenly and gets absorbed unevenly. The equator gets blasted with direct sunlight. The poles get it at a shallow angle that spreads the same energy over a much larger area. Dark ocean water absorbs heat like a sponge, while white ice sheets bounce it right back into space. And that unevenness, that imbalance, that's the engine. Weather is the atmosphere's attempt to fix an imbalance that can never actually be fixed, because the sun just keeps shining, and the Earth just keeps spinning, and the whole system never reaches equilibrium. It's always trying, always moving energy from where there's too much to where there's too little. And that constant restless effort is what we experience as wind and rain and everything else. People figured this out slowly, very slowly. For most of human history, weather was the domain of gods and spirits and omens. The Babylonians, around 650 BCE, were already trying to predict weather based on cloud patterns and astronomical observations, and honestly, they weren't terrible at it for short-term local forecasts. If you've spent your whole life farming in the same river valley, you develop an intuition for what certain cloud formations mean, what a particular shift in the wind is telling you. That's empirical knowledge, even if you're attributing it to Marduk or Enlil. The Greeks took it further. Aristotle. And you knew he was going to show up eventually, because Aristotle shows up everywhere. Wrote a treatise called Meteorologica around 340 BCE, and this is actually where we get the word meteorology. The title literally means the study of things high up, from the Greek word meteoros, meaning elevated or lofty. And Aristotle's Meteorologica is a fascinating document, not because he got things right. He got a lot of things spectacularly wrong, but because he was trying to build a systematic, rational framework for understanding atmospheric phenomena at a time when nobody had thermometers, barometers, or any way to measure what the atmosphere was actually doing. He thought wind was caused by dry exhalations from the earth being moved around by the sun's heat, which isn't exactly right, but isn't as crazy as it sounds. He was groping toward the idea that differential heating drives air movement, which is basically correct. He thought rain happened when air cooled and could no longer hold its moisture, which is remarkably close to the truth. He also thought earthquakes were caused by underground winds, and that comets were atmospheric phenomena rather than objects in space. So, mixed results. But here's what matters about Aristotle's contribution. For nearly 2,000 years after he wrote Meteorologica, that book was essentially the last word on weather science in the Western world. 2,000 years. Think about that. From roughly 340 BCE to the 1600s, if you wanted to understand weather and you were a European scholar, you were reading Aristotle. And while there were brilliant thinkers in the Islamic world and in China who made real advances during that long stretch, Arab scholars in particular preserved and expanded on Greek knowledge, and Chinese observers were recording detailed weather phenomena centuries before Europeans got around to it. The fundamental problem remained the same everywhere. You can't really do weather science without instruments. You can observe, you can theorize, you can notice patterns. But until you can actually measure temperature, pressure, humidity, and wind speed with some precision, you're essentially trying to understand a symphony by describing what the concert hall looks like from the outside. So, the real story of weather science, the story of how we went from, I think it might rain because my knee hurts, to computational models running on supercomputers that can predict the weather 7 days out with genuinely useful accuracy. That story begins in the 1600s in Italy with a series of remarkably clever people who figured out how to measure the invisible. The first breakthrough was the thermometer. Now, there's some debate about who actually invented it. Galileo Galilei built something called a thermoscope around 1593, a glass tube with a bulb at the top, partially filled with water, where the water level changed as the air in the bulb expanded or contracted with temperature. It worked, sort of, but it was also affected by atmospheric pressure, which nobody understood yet. So it was measuring two things at once without anyone realizing it. The sealed liquid in glass thermometer that we'd recognize, the kind your grandmother might have had on her porch, that came along a few decades later with contributions from several Italian instrument makers. Ferdinand II, Grand Duke of Tuscany, commissioned sealed glass thermometers filled with alcohol around 1654, and these were a genuine leap forward. For the first time, you could get a consistent, repeatable measurement of how warm or cold the air was. You could compare today to yesterday. You could compare Florence to Rome. You could start building a record. But the really transformative instrument, the one that cracked open the mystery of weather more than any other single device, was the barometer. And the story of the barometer is one of my favorite stories in all of science, because it starts with a completely practical problem that nobody could solve. In the early 1600s, Well diggers and pump operators in Italy had noticed something puzzling. When you used a suction pump to draw water up from a deep well, the water would rise about 34 feet and then just stop. No matter how good your pump was, no matter how perfectly sealed, you could not suck water higher than about 34 feet. This was a real engineering problem. Mines needed to be pumped dry, fountains needed water pressure, and this mysterious 34-foot limit was getting in the way. Galileo knew about the problem, but never fully solved it. He suggested that the vacuum created by the pump could only hold so much weight of water before it gave out, which was vaguely on the right track but not quite there. It was Galileo's student, Evangelista Torricelli, who figured it out in 1643. And his reasoning was beautiful. He thought, what if it's not the vacuum pulling the water up? What if it's the atmosphere pushing the water down into the well and then up the pipe? What if the air has weight, and that weight is pressing on the surface of the water, and the column of water in the pipe rises until its weight exactly balances the weight of the air pressing down outside? If that's true, then the 34-foot limit isn't a property of vacuums. It's a measurement of how heavy the atmosphere is. To test this, Torricelli did something clever. Instead of water, he used mercury, which is about 13.6 times denser than water. If the atmosphere can support a 34-foot column of water, it should support a column of mercury that's 34 divided by 13.6 feet tall, roughly 30 inches, or about 760 millimeters. So he filled a glass tube, sealed at one end with mercury, put his thumb over the open end, flipped it upside down into a dish of mercury, and removed his thumb. The mercury slid down the tube and stopped at almost exactly 30 inches. Above the mercury, in the sealed top of the tube, was a vacuum. The first sustained vacuum ever created in a laboratory, by the way, which was a huge deal in itself. But the really important thing was what happened next. Torricelli watched the mercury level, and it changed. Not a lot, but it moved. Up a little one day, down a little the next. The atmosphere wasn't pressing down with a constant weight. Its pressure was varying, and that, right there, was the birth of weather science as we know it. Because what Torricelli had built was a barometer, literally a weight measurer from the Greek, and what he had discovered was that atmospheric pressure changes, and that those changes are connected to what the weather does. He wrote to a friend in a letter that still survives, something like, "We live submerged at the bottom of an ocean of air," which is just a gorgeous way to put it. And it's exactly right. You're lying right now at the bottom of an ocean that's about 60 miles deep, and the pressure of all that air above you is what Torricelli's mercury column was measuring. Now, Torricelli died young. He was only 39 when he passed away in 1647, just 4 years after his great experiment. But the barometer took on a life of its own. Within a few years, people across Europe were building them, watching them, and starting to notice patterns. When the mercury rose, fair weather tended to follow. When it dropped, storms were often on the way. Nobody fully understood why yet. That would take another couple of centuries of work. But the correlation was real, and it was the first time in human history that anyone had a tool that could give you a hint about what the weather was going to do before it did it. And then things got really interesting, because in 1648, just 5 years after Torricelli's experiment, a French polymath named Blaise Pascal, yes, the same Pascal you might know from mathematics or philosophy or his famous wager about God, Pascal had a brilliant idea. If the barometer works because the atmosphere has weight, then the mercury level should be lower at higher altitudes, because there's less atmosphere above you pressing down. To test this, he asked his brother-in-law, Florent Perrier, to carry a barometer up the Puy de Dôme, a mountain in central France that rises about 4,800 feet. Perrier did it on September 19th, 1648, and the results were exactly what Pascal predicted. The mercury dropped noticeably as he climbed. At the summit, it was about 3 inches lower than at the base. This was thrilling for multiple reasons. It confirmed that air has weight, it confirmed that the barometer was measuring that weight, and it revealed something else entirely. The atmosphere has structure. It's not uniform. It thins out as you go up. And that vertical structure, that layering, turns out to be absolutely critical to understanding how weather works. But I'm getting ahead of myself a little, because to really understand why the barometer matters so much for weather, we need to talk about what atmospheric pressure actually is and why it changes from place to place and hour to hour. And to do that, we need to talk about something that might seem unrelated at first, but is actually the key to the whole puzzle. We need to talk about how air moves when you heat it up, because that's really where the whole engine starts. Picture this. You've got a patch of ground, maybe a dark plowed field in the middle of summer, and the sun is beating down on it. That dark soil absorbs a lot of solar energy, and it heats the air sitting right above it. Now, when air warms up, the molecules in it start moving faster. They bounce around more, they spread out, and the air becomes less dense. Think of it like a crowd of people in a room. If everyone starts dancing wildly, they need more space, and the crowd kind of expands. Warm air does the same thing. It gets lighter, less packed together, and because it's now lighter than the cooler air surrounding it, it rises. It floats upward, the same way a hot air balloon does, for exactly the same reason. And when that warm air rises, it leaves behind a little zone of lower pressure near the surface, because there's less air pressing down there now. Meanwhile, the cooler, denser air nearby notices that gap. Well, it doesn't notice anything, obviously, but physics does, and it rushes in to fill the space. That horizontal rush of air from high pressure to low pressure, that's wind. That's literally what wind is. It's air flowing from where there's more of it to where there's less of it, driven by pressure differences, which are themselves driven by uneven heating. And this is the fundamental mechanism. This is the engine that drives almost everything you experience as weather. The sun heats the ground unevenly because some surfaces are dark and some are light, some are wet and some are dry, some are land and some are ocean. And those temperature differences create pressure differences, and pressure differences create wind, and wind moves moisture around, and moisture creates clouds and rain, and the whole thing just cascades from there. It's beautifully simple at its core, even though the details get wonderfully complicated. Now, people had intuitions about this for a long time. Sailors knew that during the day, breezes tend to blow from the sea toward the land, and at night, the pattern reverses. They didn't know exactly why, but they could feel it. What's happening is that during the day, the land heats up faster than the ocean. Water has a much higher heat capacity, meaning it takes more energy to change its temperature. So the air over the land warms and rises, and cooler ocean air rushes in to replace it. That's your sea breeze. At night, the land cools off faster. The ocean is now relatively warmer, and the circulation flips. Simple, elegant, and it happens every single day along coastlines all over the world. But here's where it scales up in a way that really matters. Take that same basic principle, differential heating causing air to rise in one place and sink in another, and apply it to the entire planet. The equator gets far more direct sunlight than the poles, so equatorial air heats up, rises, and creates a massive low-pressure zone girdling the Earth. That rising air has to go somewhere, so it flows toward the poles at high altitude, cools down, sinks, and flows back toward the equator near the surface. In theory, you'd get one giant circulation cell in each hemisphere, warm air rising at the equator, flowing poleward, sinking at the poles, and returning. And a brilliant man named George Hadley figured this out in 1735. Hadley was an English lawyer, which is a detail I love because it reminds you that some of the most important insights in science have come from people working outside the formal boundaries of the field. He was a lawyer by profession, but deeply curious about the natural world, and he was trying to solve a specific puzzle. Why do the trade winds blow the way they do? Sailors had known for centuries that in the tropics, the prevailing winds blow from east to west. These trade winds were the lifeblood of global commerce. They're the reason the sailing routes between Europe and the Americas followed particular paths. But nobody had a convincing explanation for why they blew so reliably in that direction. Hadley's insight was twofold. First, he understood the thermal circulation, hot air rising at the equator, cooler air flowing in from higher latitudes to replace it. That gives you a north-south component. But he also realized that the Earth's rotation matters. As air flows from, say, the subtropics toward the equator, the Earth is spinning underneath it. And because the Earth's surface moves faster at the equator than at higher latitudes, the equator is the widest part of the spinning sphere. So a point on the equator has to travel a greater distance in 24 hours. The air can't quite keep up. From the perspective of someone standing on the ground, the air appears to curve. In the northern hemisphere, it curves to the right. In the southern hemisphere, it curves to the left. This is what we now call the Coriolis effect, though Hadley didn't have that precise mathematical framework. The full mathematical description came later from a French scientist named Gaspard Gustave de Coriolis, who published his work on rotating reference frames in 1835, a full century after Hadley's paper. And here's what's really clever about this combination. The thermal drive pushes air from the subtropics toward the equator. The Coriolis effect turns that flow to the right in the northern hemisphere. So instead of blowing straight south toward the equator, the wind ends up blowing from the northeast. And that's exactly what the trade winds do. In the southern hemisphere, the same logic gives you winds from the southeast. Hadley had cracked it. Not perfectly. His model was too simple in some ways, and the real atmosphere is more complicated. But the core insight was right, and the tropical circulation cell that bears his name, the Hadley cell, is one of the most important features of Earth's climate system. Now, I should mention that Hadley's single-cell model, one big loop from equator to pole in each hemisphere, doesn't actually work for the whole atmosphere. The circulation breaks up into 3 cells per hemisphere. You've got the Hadley cell in the tropics, extending from the equator to about 30 degrees latitude. Then there's the Ferrel cell in the mid-latitudes, from about 30 to 60 degrees, which actually circulates in the opposite direction. And then the polar cell from 60 degrees to the pole. This 3-cell model was worked out over time by various scientists, and it's still a simplification, but it captures the essential pattern. The boundaries between these cells are where a lot of interesting weather happens. The subtropical high-pressure zones around 30 degrees, where the world's great deserts tend to be, and the polar front around 60 degrees, where cold polar air meets warmer mid-latitude air. and storms breed. But I'm jumping ahead a bit. Let's come back to the 1700s, because the story of weather science in that century is really a story about instruments getting better and people starting to collect data systematically. The thermometer improved enormously. Daniel Gabriel Fahrenheit, a Polish-born German physicist, developed the first reliable mercury thermometer around 1714. Mercury was a much better working fluid than alcohol. It expands more uniformly with temperature. It doesn't stick to the glass, and it has a much wider useful range. Fahrenheit also established his temperature scale, with 32 degrees for the freezing point of water and 212 for the boiling point. A few decades later, in 1742, the Swedish astronomer Anders Celsius proposed his own scale, originally with 100 for freezing and 0 for boiling, which was later inverted to the form we use today. These might seem like small details, but standardized temperature scales were revolutionary. For the first time, a temperature reading in London could be meaningfully compared with one in Paris or Stockholm. You could start building a picture of how temperature varied across the continent, across the seasons, across altitudes. And the barometer was improving too. Robert Hooke in England, one of the most inventive minds of the 17th century. The man was involved in everything from microscopy to architecture to the theory of elasticity. Hooke developed a wheel barometer that was easier to read than Torricelli's simple tube design. He also started keeping systematic weather records, noting the barometric pressure alongside wind direction, temperature, and sky conditions. This was around the 1660s and 1670s. Hooke even proposed a standardized system for recording weather observations with specific symbols for different conditions. He was, in many ways, trying to invent meteorological data collection before anyone really knew what to do with the data. And that's the thing. Having instruments was only half the battle. The other half was figuring out what the measurements meant when you put them all together. A single barometer reading tells you the pressure at one spot at one moment. But weather is a vast, three-dimensional, constantly changing system. To understand it, you need readings from many places at the same time, and you need to see how they change over hours and days. You need a network, and building that network, convincing people across cities and countries to take measurements in the same way, at the same times, with calibrated instruments, and then somehow getting all that data to one place. That was an enormous logistical challenge. It was a challenge that wouldn't really be solved until something else came along, something that had nothing to do with weather science at all, but changed it forever. And that something was the electric telegraph, which burst onto the scene in the 1840s and suddenly made it possible to transmit weather observations across hundreds of miles in minutes instead of days. But before we get to that transformation, there's another piece of the puzzle that was being worked out during the 1700s and early 1800s, a piece that involves water in ways you might not expect, and it starts with a deceptively simple question. What actually happens when water evaporates? And where does all that energy go? Because it turns out that the answer to that question is one of the most important keys to understanding weather, and it was hiding in plain sight for centuries. Think about boiling a pot of water on your stove. You turn on the heat, the water gets warmer and warmer, and then it reaches 100 degrees Celsius, and it starts to boil. But here's something you might have noticed without really thinking about it. Once the water starts boiling, the temperature doesn't keep going up. You can crank the burner as high as it'll go, and the water stays right at 100 degrees. It boils faster, sure, more bubbles, more steam. but the thermometer doesn't budge. So where is all that extra heat energy going? It's going into the water molecules themselves, giving them enough energy to break free of the liquid and become gas, steam, water vapor. That energy doesn't disappear. It gets absorbed into the vapor, carried along with it, hidden inside it. And the beautiful term for this is latent heat, from the Latin word for hidden. The heat is there, it's real energy, but you can't measure it with a thermometer because it's not raising the temperature of anything. It's been tucked away into the change of state itself, from liquid to gas. Now, the person who really nailed down the science of this was a Scottish chemist named Joseph Black, working in the 1750s and 1760s at the University of Glasgow. Black was meticulous, the kind of thinker who noticed the things everyone else walked right past. He realized that heat and temperature were not the same thing, which sounds obvious now, but was genuinely confusing to people at the time. He showed that when ice melts, it absorbs a large amount of heat without changing temperature, and when water boils, it absorbs even more heat without changing temperature. He called this latent heat, and he distinguished between the latent heat of fusion, the energy absorbed when ice becomes liquid water, and the latent heat of vaporization, the much larger amount of energy absorbed when liquid water becomes vapor. And here's what matters for weather. The latent heat of vaporization for water is enormous. It takes about 2,260 joules of energy to turn a single gram of liquid water into vapor at 100 degrees. But evaporation doesn't only happen at the boiling point. It happens all the time, at any temperature, whenever water molecules at the surface have enough energy to escape into the air. That's what's happening when a puddle dries up on a warm afternoon, when the ocean surface shimmers under the sun, when your wet hair slowly dries. Water is constantly evaporating from oceans, lakes, rivers, soil, and plants, and every single gram of it carries that hidden energy up into the atmosphere. Now think about the scale of this. The sun is pouring energy onto the Earth's surface, and a huge fraction of that energy goes into evaporating water, especially over the tropical oceans where the sun hits hardest. All that latent heat gets loaded into water vapor and carried upward and sideways by the wind. The atmosphere becomes this vast reservoir of hidden energy, and you can't see it, you can't feel it as warmth. It's just humid air. But then something happens. That moist air rises, it cools as it expands at higher altitudes, and eventually the water vapor condenses back into tiny liquid droplets. That's what a cloud is, billions of tiny water droplets or ice crystals. And when that vapor condenses, all the latent heat that was hidden inside it gets released. Suddenly you have this burst of warming in the atmosphere, right there inside the cloud, and that warming makes the air even more buoyant, so it rises faster, which pulls in more moist air from below, which condenses and releases more heat, and you get this self-reinforcing cycle. That's the engine that drives thunderstorms. That's the engine that drives hurricanes. Latent heat is the fuel. And this is one of those ideas that, once you really grasp it, changes how you see the whole system. Weather isn't just about the sun heating the ground and the ground heating the air. It's about the sun heating the ocean evaporating water, the water vapor carrying energy invisibly through the atmosphere and then releasing it somewhere else, maybe hundreds or thousands of miles away, when it condenses into clouds and rain. It's an energy transport system of staggering scale, and water is the vehicle. Joseph Black, by the way, had a young instrument maker working in his lab at Glasgow, a fellow named James Watt, and Black's ideas about latent heat directly influenced Watt's thinking about steam engines. The connection between understanding weather and understanding engines isn't a coincidence. They're both about heat, phase changes, and energy transfer. The same physics that powers a hurricane powers a steam turbine. But let's come back to the atmosphere. So you've got this picture now. The sun drives evaporation. The vapor rises, condenses into clouds, releases heat, and falls back as rain or snow. This cycle has a name, of course. It's the water cycle, or the hydrological cycle. And it's one of those things you probably learned about in school with a nice neat diagram showing arrows going up and coming down. But the real water cycle is messy and complicated and driven by all these interacting forces: differential heating, pressure gradients, the Coriolis effect, the distribution of land and ocean, mountain ranges that force air upward, cold ocean currents that suppress evaporation. All of it feeds into where clouds form, where rain falls, and where deserts persist. And speaking of clouds, here's where another fascinating character enters the story. Luke Howard was a London pharmacist, an amateur meteorologist, and in 1802, he gave a lecture to a small scientific society in London that would change how we talk about the sky forever. Howard proposed a classification system for clouds. Before him, clouds were just clouds. People described them vaguely: dark ones, fluffy ones, thin ones, rain ones. Howard looked up and saw order. He identified 3 basic forms and gave them Latin names. Cumulus, from the Latin for heap or pile. Those are the puffy, cotton ball clouds you see on a nice summer day, flat on the bottom, billowing on top. Stratus, from the Latin for layer. Those are the flat, gray, sheet-like clouds that cover the whole sky like a blanket. And cirrus, from the Latin for curl or wisp. Those are the thin, feathery, high-altitude clouds made of ice crystals. Howard also recognized that clouds could combine forms and transition between them. He described cumulonimbus, the towering thunderstorm cloud, and cirrostratus, the thin, high veil that sometimes puts a halo around the sun or moon. His system was elegant and practical, and it caught on remarkably fast. Goethe, the great German writer and polymath, was so taken with Howard's cloud classification that he wrote poems about it. Literally, wrote poems dedicated to Luke Howard. And here's the thing that makes Howard's system so clever. It wasn't just naming shapes for the sake of naming them. Each cloud type tells you something about what's happening in the atmosphere. Cumulus clouds form when warm air rises in discrete bubbles or columns. They're signs of convection, of the atmosphere being heated from below. The flat bottom of a cumulus cloud marks the altitude where the rising air has cooled enough for its moisture to condense. Every cumulus cloud is basically showing you the condensation level, painted right there in the sky. Stratus clouds form when a whole layer of air is lifted gently, maybe by sliding over a wedge of cooler air, or by being pushed gradually up a mountain slope. They tell you about stable, widespread lifting rather than vigorous convection. Cirrus clouds are way up high, 6 or 8 kilometers, where it's so cold that water exists only as ice. Those wispy streaks you see are actually ice crystals being blown sideways by high-altitude winds, and the shape of cirrus clouds can tell you about wind speed and direction in the upper atmosphere. Pilots and early aviators learned to read cirrus clouds for clues about what was coming. So Howard gave us a language for the sky, and that language was rooted in physics. And this matters for forecasting, because different cloud types are associated with different weather patterns. When you see high cirrus clouds thickening into cirrostratus, followed by lower and thicker altostratus, and then dark nimbostratus rolling in, that sequence often means a warm front is approaching, a mass of warm air sliding up over cooler air, and rain is probably 6 to 12 hours away. Generations of farmers, sailors, and eventually professional meteorologists learned to read these cloud progressions like a story being told in slow motion across the sky. Now, around the same time Howard was classifying clouds, other scientists were working on the bigger puzzle of how air masses interact. And this brings us to one of the most important concepts in all of weather science, the idea of fronts. But the word front wouldn't be coined until much later, during and after World War I, by a group of Norwegian meteorologists who quite deliberately borrowed the term from military language because they saw air masses clashing like armies along battle lines. That group, centered in Bergen, Norway, would revolutionize weather forecasting in ways that still shape how your local forecast is made today. But their story belongs a little further along in our journey. What was happening in the early 1800s was a growing realization that weather systems were organized, that storms had structure, that they moved in somewhat predictable paths, and that if you could see the whole picture, pressure readings, wind directions, temperatures, cloud types, from many locations at once, you might actually be able to predict what was coming. The instruments existed. The classification systems were being developed. The physics of heat, evaporation, and pressure were increasingly understood. What was still missing was the ability to gather all that information fast enough to be useful. A storm that takes 12 hours to reach you doesn't care that your weather report will arrive by mail in 3 days. And that's exactly why the electric telegraph changed everything. When Samuel Morse sent his famous first message, "What hath God wrought?" along a wire from Washington to Baltimore in May of 1844, he was thinking about communication, about business, about connecting people. He probably wasn't thinking about weather. But within just a few years, scientists and government officials realized that the telegraph could do something that had never been possible before in human history. It could make weather observations from distant cities available in real time. You could know what the weather was doing in Pittsburgh and Cincinnati and St. Louis right now, not 2 days ago. And if you saw a storm moving eastward through those cities, you could warn Philadelphia and New York that it was coming. The person who seized on this idea with the most energy and ambition was a man named Joseph Henry, the first secretary of the Smithsonian Institution in Washington, D.C. Henry was a brilliant physicist in his own right. He'd done pioneering work on electromagnetism, and when he took charge of the Smithsonian in 1846, he had a vision. He began recruiting volunteer observers across the United States, equipping them with standardized instruments, and asking them to telegraph their weather observations to Washington every day. By the mid-1850s, Henry had a network of around 150 observers, and he created a large map of the United States in the Smithsonian's Great Hall, updating it daily with colored cards showing current conditions at each station. Visitors could walk in and see, for the first time, a real-time picture of weather across an entire continent. This was extraordinary. For all of human history, weather had been local. You knew what was happening overhead, and you could guess at what might be coming based on wind direction and cloud types and the ache in your grandfather's knee. But now, suddenly, you could see the system. You could see that a band of rain stretched from Tennessee to Ohio. That high pressure sat over the Great Plains, that winds were shifting along the coast. The map made weather visible as a continental phenomenon, and it made the idea of forecasting, actually predicting what would happen tomorrow, seem not just possible, but inevitable. And it wasn't just happening in America. Across the Atlantic, a man with one of the most dramatic life stories in all of science was building a similar system, driven not by academic curiosity, but by tragedy at sea. His name was Robert Fitzroy, and if that name sounds familiar, it might be because he was the captain of HMS Beagle, the ship that carried a young Charles Darwin around the world on the voyage that would lead to the theory of evolution. Fitzroy was a brilliant navigator, a meticulous observer, and a deeply complicated man. After his naval career, he was appointed in 1854 to head a new department within the British Board of Trade, tasked with collecting weather data from ships at sea. But Fitzroy wasn't content to just collect data. He wanted to use it. He wanted to save lives. And the event that crystallized his mission was a devastating storm in October 1859, the Royal Charter Storm. A massive cyclone swept across the British Isles on the 25th and 26th of that month, and it was catastrophic. The Royal Charter itself was an iron-hulled clipper ship returning from the Australian gold rush, packed with passengers and cargo, including a substantial amount of gold. She was just hours from completing her voyage, approaching the coast of Anglesey in Wales, when the storm hit with extraordinary violence. Winds that may have exceeded 100 miles per hour drove the ship onto rocks near the village of Moelfre. Over 450 people died that night. Bodies washed ashore for days. And the Royal Charter was just the most famous casualty. Across the British Isles, over 200 ships were wrecked or damaged in that single storm, and around 800 lives were lost in total. Fitzroy was devastated. He had the meteorological data. He had barometric readings from stations across the country, and when he went back and looked at the pressure patterns in the days leading up to the storm, he could see it coming. The signs were there. A deep drop in pressure moving in from the Atlantic, a tightening gradient that screamed danger. But there had been no system in place to warn anyone. The information existed, but it arrived too late, scattered in logbooks and station records that nobody synthesized in time. Those sailors didn't have to die. That was the thought that consumed Fitzroy, and it drove him to do something no government official had ever done before. He decided to issue storm warnings. Starting in February 1861, Fitzroy established a system where weather observations from telegraph stations around the British coast were sent to his office in London each morning. He analyzed the data, identified dangerous patterns, and when he believed a storm was approaching, he telegraphed warnings to ports, where visual signals, cones and drums hoisted on masts, told sailors whether to expect a gale from the north or the south. Think about what a leap that was. A government office was telling people what the weather was going to do before it happened. And then, in August of that same year, Fitzroy went even further. He began publishing daily weather forecasts in the Times newspaper. He actually coined the word forecast. He chose it deliberately, wanting to distinguish what he was doing from prophecy or mere guessing. A forecast, in his mind, was a reasoned projection based on data and physical understanding. And here's the thing, his forecasts were often right, not always, but often enough to be genuinely useful. Sailors paid attention. Port authorities paid attention. But the scientific establishment? They were deeply skeptical. And honestly, from a certain perspective, you can understand why. Fitzroy didn't have equations governing atmospheric motion. He didn't have a complete physical theory of weather systems. He was working from pattern recognition, from his extraordinary experience at sea, from an intuitive grasp of how pressure systems behaved. His methods were partly empirical, partly instinctive, and he couldn't always explain precisely why he made a particular prediction. To the rigorous scientists of the Royal Society, this looked uncomfortably like guesswork dressed up in official authority. When his forecasts were wrong, and sometimes they were spectacularly wrong. The criticism was savage. Newspapers mocked him. Fellow scientists questioned his competence. The fishing industry complained that false storm warnings cost them money when boats stayed in port unnecessarily. The pressure on Fitzroy was immense, and it compounded other burdens he carried. He had always been prone to depression. It ran in his family, tragically. His uncle, Viscount Castlereagh, had died by suicide. Fitzroy had struggled with mental health even during the Beagle voyage, and Darwin himself had worried about him. The combination of professional humiliation, overwork, financial strain, and what seems to have been a deep constitutional vulnerability proved too much. On April 30th, 1865, Robert Fitzroy took his own life. He was 59 years old. It's one of the saddest stories in the history of science. A man who genuinely wanted to save lives, who built a system that was fundamentally on the right track, destroyed by the gap between what he could see intuitively and what he could prove formally. After his death, the forecasts were suspended. The scientific establishment got its way. No more predictions without rigorous theory. The storm warnings continued, because even the skeptics couldn't argue with the basic principle of telegraphing dangerous pressure drops to ports. But the daily forecasts in the Times stopped, and sailors went back to facing the weather with less warning than they'd had before. The forecasts would eventually return, of course. But Fitzroy's story illuminates something really important about the science of weather at this point in history. The observations were getting better. The telegraph networks were growing. People could see weather patterns moving across maps. But the fundamental question, why does the atmosphere do what it does, and how can we predict it mathematically, remained wide open. And answering that question would require a completely different kind of thinking. So let's talk about that. Let's talk about the physics of weather, not just the observation of it. Because in the second half of the 19th century and into the early 20th, a handful of people started trying to write down the actual equations that govern atmospheric motion. And this is where things get both beautiful and incredibly hard. You already know the basic ingredients. The sun heats the surface unevenly. That creates pressure differences. Pressure differences drive wind. The Coriolis effect from Earth's rotation deflects that wind. Water evaporates, rises, condenses, releases latent heat, and that heat drives more motion. All of these processes obey the laws of physics, Newton's laws of motion, the laws of thermodynamics, the principles of fluid dynamics. In theory, if you could write down all the relevant equations and solve them, you could predict exactly what the atmosphere would do next. The problem is that the atmosphere is a fluid, a compressible, rotating, heated from below, unevenly bounded fluid covering a sphere. And the equations governing fluid motion are, to put it mildly, not easy. The fundamental equations are called the Navier-Stokes equations, named after Claude Louis Navier, a French engineer who derived an early form in 1822, and George Gabriel Stokes, an Irish-British mathematician who refined them in the 1840s. These equations describe how velocity, pressure, temperature, and density in a fluid all relate to each other and change over time. They're partial differential equations, and they're nonlinear, which is the mathematical way of saying that the different variables don't just add up neatly. They multiply and interact with each other in ways that make the equations extraordinarily difficult to solve. Here's an analogy that might help. Imagine you're trying to predict where a leaf will go when you drop it into a stream. If the stream is perfectly smooth and laminar, just flowing in nice straight lines, you could probably work it out. But real streams have eddies and turbulence, rocks that create vortices, places where the flow speeds up and slows down. The leaf's path depends on every little swirl, and every swirl depends on every other swirl. That's what the atmosphere is like, except it's three-dimensional. It covers the entire planet, and the stream is being heated and cooled and spun and disrupted by mountains and oceans and ice caps. The Navier-Stokes equations capture all of this in principle, but solving them for any realistic situation? Nobody has ever done it exactly. In fact, proving whether smooth solutions even always exist for these equations is one of the 7 Millennium Prize problems in mathematics. There's literally $1 million bounty on it, and it remains unsolved as of today. So the atmosphere obeys known physical laws, but those laws generate equations that are essentially impossible to solve by hand for real-world conditions. That's the fundamental challenge of weather prediction, and it's why Fitzroy couldn't provide the mathematical rigor his critics demanded. The rigor existed in principle. The equations were there, but the tools to work with them didn't exist yet. The person who first seriously attempted to bridge that gap was a remarkable Englishman named Lewis Fry Richardson, and his story is one of the most extraordinary in all of science because he tried to do something that was simultaneously visionary and completely, hilariously impractical. Richardson was a Quaker, a pacifist, a mathematician, and a deeply original thinker. During World War I, he served as an ambulance driver with the Friends ambulance unit in France. He wouldn't fight, but he would help. And in the trenches and rest stations of the Western Front, in whatever spare moments he could find between carrying wounded men, he worked on a problem that had never been attempted before. He tried to compute a weather forecast from first principles. His idea was conceptually straightforward, even if the execution was monstrous. Take the atmosphere over a region. He chose a section of Central Europe and divide it into a grid of columns. Each column represents a chunk of atmosphere at a particular location. For each column, write down the current conditions: pressure, temperature, humidity, wind speed, and direction at various altitudes. Then, using the equations of motion and thermodynamics, calculate how those conditions would change over a short time step. Say, 6 hours. The new conditions in each column depend on what's happening in neighboring columns, because air flows between them. So you do the calculation for every column simultaneously, step forward in time, and repeat. This is, in essence, exactly how modern weather forecasting works. Richardson invented the concept of numerical weather prediction. He laid it out in a book published in 1922 called Weather Prediction by Numerical Process, and it's a work of staggering ambition. He actually carried out the calculation by hand for a single time step, for a single forecast, covering a limited area. It took him weeks, and the result was completely wrong. His forecast predicted a pressure change of 145 millibars in 6 hours, which would be an apocalyptic, physically impossible event. The actual pressure change was nearly zero. Now, you might think that would be discouraging, and it was, a little. But Richardson understood why it failed. The initial data was too coarse. Small errors in the starting conditions got amplified by the calculations. The grid was too rough, the time step too large, and some of the mathematical techniques he used introduced instabilities. He knew the method was sound even if the execution was beyond what any human could manage by hand. And here's the part that shows you just how far ahead of his time Richardson was thinking. In his book, he imagined what it would take to produce weather forecasts in real time using his method. He envisioned a vast hall. He called it a forecast factory, filled with 64,000 human computers, each one responsible for calculating the equations for one small section of the atmosphere, all coordinated by a conductor in the center who kept them synchronized, like an orchestra. It's a breathtaking image. 64,000 people doing arithmetic in parallel to keep pace with the weather itself. It was science fiction in 1922. But what Richardson was describing, without knowing it, was a massively parallel computer. He just didn't have the machine yet. And that's the crucial bottleneck that would define weather science for the next 3 decades. The theory was there. The equations were known. The method, divide the atmosphere into a grid, apply the physics, step forward in time, was laid out clearly. But the sheer volume of calculation required was beyond any human effort. You needed something that could perform millions of arithmetic operations quickly and without error. You needed a machine that didn't exist yet, and the person who would finally build that machine and use it to produce the first successful numerical weather forecast was one of the most brilliant and controversial figures of the 20th century, a Hungarian-American mathematician whose work touched everything from quantum mechanics to game theory to the atomic bomb. His name was John von Neumann, and his interest in weather prediction wasn't purely academic. He believed that if you could model the atmosphere mathematically, you might eventually be able to control it, to actually reach into the atmosphere and steer it, suppress a hurricane before it made landfall, break a drought by triggering rain exactly where you wanted it, maybe even weaponize the weather against an enemy. Von Neumann wasn't shy about this. He saw weather control as a logical extension of weather prediction, and he thought both were within reach if you had enough computational power, which, conveniently, was exactly what he was building. Let's talk about von Neumann for a moment, because he's one of those figures who shows up in so many different corners of 20th century science that it almost feels like he was several people. Born in Budapest in 1903, he was a genuine prodigy, the kind of person whose childhood stories sound exaggerated, but apparently aren't. By age 6, he could divide 8-digit numbers in his head. By his 20s, he'd already made significant contributions to set theory, quantum mechanics, and mathematical logic. He emigrated to the United States in 1930, joined the Institute for Advanced Study in Princeton, the same institution where Einstein worked, and during World War II, he became deeply involved in the Manhattan Project, helping design the implosion mechanism for the plutonium bomb. He was, by all accounts, extraordinarily fast at seeing mathematical structures in physical problems and figuring out how to compute solutions. And it was during the war that von Neumann became interested in electronic computing. He worked closely with the team-building ENIAC, the electronic numerical integrator and computer, at the University of Pennsylvania, one of the first general-purpose electronic computers. ENIAC was enormous, filling an entire room, using about 18,000 vacuum tubes, and it was designed primarily to calculate artillery firing tables for the Army. But von Neumann immediately saw that machines like this could do far more. He wrote a famous document in 1945 describing the architecture for a stored program computer, a machine that could hold its instructions in memory and modify them during execution. This is essentially the architecture that every modern computer still uses. It's called the von Neumann architecture, and if you're listening to this on a phone or a laptop, you're using a descendant of that idea right now. So here was a man who understood both the mathematical structure of atmospheric physics and the emerging power of electronic computation. And sometime around 1946, he put those two things together. Von Neumann proposed to the Institute for Advanced Study that they build their own computer, not for abstract mathematics, but for a specific, ambitious application: numerical weather prediction. He argued that weather forecasting was the perfect problem for electronic computing. It was scientifically important, it was practically useful, and it required exactly the kind of massive, repetitive calculation that computers were good at and humans were terrible at. And he got the funding. Now, von Neumann was a mathematician, not a meteorologist. He needed someone who understood the atmosphere, and the person he found was Jules Charny, a young American meteorologist who would become one of the most important figures in the history of weather science. Charny was born in San Francisco in 1917, studied at UCLA, and by his late 20s had already done brilliant theoretical work on the dynamics of large-scale atmospheric waves. He understood something crucial that Richardson, back in 1922, hadn't fully grasped. And this is really the key to why Richardson's forecast had failed so spectacularly. Here's the thing. Remember how Richardson divided the atmosphere into a grid and tried to step forward using the full equations of motion? The problem was that the atmosphere contains many different kinds of motion happening simultaneously. You've got the big, slow-moving weather systems, the highs and lows, the fronts, the storms that take days to cross a continent. But you've also got fast-moving sound waves and gravity waves rippling through the atmosphere at hundreds of meters per second. These fast waves carry almost no weather information. They're basically noise from a forecasting perspective, but they're real solutions to the equations. And when Richardson plugged in his observed data, which had small measurement errors scattered throughout, those errors excited these fast waves in his calculation. The fast waves amplified, swamped the actual weather signal, and his forecast blew up. That's why he predicted a pressure change of 145 millibars in 6 hours when the real atmosphere barely changed at all. It wasn't that his method was wrong in principle. It was that the full equations were too sensitive to small errors in the initial data, because those errors fed energy into motions that didn't matter for weather, but dominated the math. Charny's insight was that you could filter out these troublesome fast waves by simplifying the equations. Instead of using the complete Navier-Stokes equations, you could use a reduced set, what became known as the quasi-geostrophic equations, that only described the large-scale, slow-moving patterns relevant to actual weather. By mathematically filtering out the sound waves and gravity waves, you removed the mechanism that had caused Richardson's forecast to explode. It was an elegant solution. You were deliberately throwing away some of the physics, but the physics you were throwing away was irrelevant to the forecast. What remained was a set of equations that were simpler, more stable, and still captured the essential behavior of weather systems. Think about what that means. Sometimes the path forward in science isn't adding more detail, it's figuring out what you can safely ignore. Charny understood which motions mattered and which were just mathematical noise, and by building a model that only included the important ones, he made the problem tractable. So in the late 1940s, Charny assembled a small team at the Institute for Advanced Study in Princeton, working alongside von Neumann's computer project. The computer they used was called the IAS machine, sometimes informally called the Maniac, though that name is a bit tangled with other machines of the era. It was one of the first stored program computers, built largely to von Neumann's specifications, and it was, by modern standards, astonishingly limited. It had about 5 kilobytes of memory. 5 kilobytes. Your phone has roughly 1 million times more. But it could perform arithmetic operations far faster than any human, and that was what mattered. In the spring of 1950, Charny and his team, which included the Norwegian meteorologist Ragnar Fjørtoft and von Neumann himself, ran their first numerical weather forecasts on the ENIAC computer at the Aberdeen Proving Ground in Maryland. They actually used ENIAC rather than the IAS machine for this first attempt because the IAS computer wasn't quite finished yet. ENIAC was already operational, and although programming it was a nightmare, you had to physically rewire parts of the machine for each new problem. It had the raw computational power they needed. They chose to forecast the movement of the 500 millibar pressure surface, essentially the pattern of ridges and troughs in the middle atmosphere, about 5.5 kilometers up. This is a standard level that meteorologists use because the flow patterns there strongly influence the weather at the surface. They used Charney's filtered equations, set up a grid covering North America, fed in observed data from weather stations, and let the machine calculate 24-hour forecasts. And it worked. Not perfectly. The forecasts had significant errors, and they certainly weren't as good as what an experienced human forecaster could produce by studying weather maps and using intuition built up over years. But the predicted patterns were recognizably correct. The large-scale features, where the troughs and ridges were, how they moved, showed up in roughly the right places. For the first time in history, a machine had taken raw atmospheric data, applied the laws of physics through numerical calculation, and produced a weather forecast that bore a meaningful resemblance to what actually happened. The calculation itself took about 24 hours to produce a 24-hour forecast, so it wasn't yet fast enough to be operationally useful. You'd have the forecast at the same time the weather was already happening. But that was a speed problem, not a science problem. Computers were getting faster every year. The fundamental proof of concept was there. Richardson's dream, articulated in 1922, had finally been realized in 1950. Numerical weather prediction was real. And here's what's quietly beautiful about this moment. Richardson was still alive. He was 70 years old, living in quiet retirement, and he got to see it happen. He got to see the method he'd invented, the method that had failed so dramatically when he tried it by hand in a French farmhouse during World War I, vindicated by an electronic computer 3 decades later. Charney and his colleagues explicitly acknowledged Richardson's pioneering work. The old Quaker ambulance driver, who'd been laughed at for predicting a 145 millibar pressure change, had been right about everything, except the computational resources available to him. Von Neumann, meanwhile, was already thinking bigger. He wanted to move beyond simple forecasting into understanding the general circulation of the atmosphere, the global patterns of wind and weather that emerge from the fundamental physics. And beyond that, he still harbored his dream of weather control. In a 1955 article for Fortune magazine, he wrote about the possibility of deliberately modifying weather patterns, suggesting that relatively small interventions at the right place and time could have large effects on atmospheric behavior. He was thinking about what we'd now call sensitive dependence on initial conditions, though he saw it as an opportunity rather than a limitation. If small changes could have big effects, then maybe you could steer the atmosphere where you wanted it to go. Von Neumann died young, in 1957, of cancer likely related to his radiation exposure during nuclear weapons tests. He was only 53. He didn't live to see just how thoroughly his vision of computational weather prediction would transform the field. And he didn't live to see the discovery that would fundamentally undermine his dream of weather control, a discovery made by a quiet, meticulous meteorologist working alone with a very simple computer model in the early 1960s. That meteorologist's name was Edward Lorenz, and what he stumbled onto, almost by accident, would change not just weather science, but our entire understanding of predictability itself. Lorenz was not the kind of person who sought the spotlight. Born in 1917 in West Hartford, Connecticut, he was quiet, almost shy, the kind of scientist who preferred to let his equations do the talking. He'd studied mathematics at Dartmouth and Harvard before the Second World War pulled him sideways into meteorology. The military needed weather forecasters, desperately, and Lorenz was trained at MIT as part of the Army Air Corps program. After the war, he stayed. Something about the atmosphere had gotten under his skin. He earned his doctorate in meteorology at MIT and joined the faculty there, and by the late 1950s, he was doing exactly the kind of work von Neumann had championed, using computers to simulate atmospheric behavior. But Lorenz's computer was nothing like ENIAC. By 1960, he had a Royal McBee LGP-30 sitting in his office, a desk-sized machine that was, by the standards of the day, modest. It had about the computing power of a decent pocket calculator from the 1980s. But it was enough for what Lorenz wanted to do, which was run a highly simplified model of atmospheric convection. Just 12 equations governing the relationships between temperature, pressure, and wind in a stripped-down, idealized atmosphere. He wasn't trying to forecast real weather. He was trying to understand the general behavior of weather-like systems. How do patterns form? How do they evolve? What makes them change? And here's where the famous accident happened. One day, in the winter of 1961, Lorenz wanted to rerun a particular simulation, but instead of starting it over from the beginning, he decided to save time by starting from the middle. He'd printed out the numbers from an earlier run, so he typed them back in and let the computer continue from that point. Then he went down the hall to get a cup of coffee. When he came back, the new run had diverged completely from the original. The weather patterns that the model was producing were utterly different from what they'd been the first time around. At first, he thought the computer had malfunctioned, but then he looked more carefully at what he'd done. The computer stored numbers internally to 6 decimal places, so a value might be 0.506127. But the printout, to save space on the paper, only showed 3 decimal places, 0.506. When Lorenz typed the numbers back in, he'd rounded them. The difference was tiny, less than 1 part in 1,000, and yet that minuscule difference had amplified and amplified and amplified until the two simulations bore no resemblance to each other. Think about what that means. Think about what that really means. You have a deterministic system, meaning the equations have no randomness in them at all. Every output is completely determined by the inputs, and yet you cannot reproduce the output unless your inputs are perfect. Not approximately perfect. Not very, very close. Perfect. Because any deviation, no matter how small, will eventually grow until the two trajectories are completely unrelated. This is what we now call sensitive dependence on initial conditions, and it's the heart of what became chaos theory. Lorenz didn't use the word chaos right away. That term was coined later by the mathematician James York in 1975. But Lorenz understood immediately what he'd found, and he understood its implications for weather forecasting. If the atmosphere behaves like his model, and there was every reason to think it did, since the real atmosphere is far more complex, with far more variables and far more nonlinearity, then perfect long-range weather prediction is fundamentally impossible. Not because we don't have good enough computers, not because we don't understand the physics well enough, but because we can never measure the current state of the atmosphere with infinite precision. There will always be tiny errors in our observations. A temperature reading that's off by 1/10 of a degree, a wind measurement that's slightly wrong, a patch of ocean we didn't sample. And those tiny errors will grow. They'll double and double again, and eventually they'll overwhelm the forecast. Lorenz published his findings in 1963 in a paper called Deterministic Non-Periodic Flow in the Journal of the Atmospheric Sciences. It's one of the most important scientific papers of the 20th century, though almost nobody noticed it at the time. Meteorologists weren't reading about dynamical systems theory, and mathematicians weren't reading atmospheric science journals. The paper sat there, quietly revolutionary, for years before its significance was widely recognized. But here's what's really beautiful about what Lorenz discovered. He didn't just show that prediction breaks down. He showed that there's a structure to the unpredictability. When he plotted the trajectories of his simplified system in three-dimensional space, they traced out a shape, not a random scribble, but a specific, intricate, endlessly looping form that never quite repeated itself. Two wings, like a butterfly's, with the trajectory spiraling around one wing for a while, then flipping to the other, then back, in a pattern that was deterministic but never periodic. This shape became known as the Lorenz attractor, and it's one of the iconic images of modern science. Though of course you're lying there with your eyes closed. So just picture it as a kind of three-dimensional figure 8 that's been stretched and twisted, with the path winding around and around but never crossing itself, never settling down, never repeating. And that phrase, butterfly, leads us to the most famous metaphor in all of chaos theory. In 1972, Lorenz gave a talk at a meeting of the American Association for the Advancement of Science, and the title of his talk, suggested by a colleague, was, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" He wasn't saying that butterflies literally cause tornadoes. He was saying that the atmosphere is so sensitive to small perturbations that, in principle, you cannot separate the influence of any single event from the rest of the system. Everything is connected. Everything matters. And that means there's a hard limit on how far ahead you can predict the weather, no matter how good your tools are. Now, this is where von Neumann's dream of weather control quietly dies. Remember what he'd written in that Fortune article? That sensitive dependence could be an opportunity? That you could nudge the atmosphere with small interventions and steer it where you wanted? Lorenz showed that the sensitivity cuts both ways. Yes, small changes have big effects, but you can't predict what those effects will be. If you seed a cloud over one city, you might prevent rain there, but cause a drought somewhere else, or trigger a storm system 1,000 miles away 3 weeks later. The atmosphere is not a machine with a steering wheel. It's a system so intricately coupled that any attempt to control it would have consequences you couldn't foresee or contain. So, what does this mean for weather forecasting in practice? Does it mean we should give up? Not at all. What Lorenz's work tells us is that there's a horizon, a predictability horizon, beyond which deterministic forecasting becomes impossible. For the real atmosphere, that horizon turns out to be somewhere around 2 weeks. Beyond about 10 to 14 days, individual weather events. Will it rain in London on a specific Tuesday? Become fundamentally unpredictable. But within that window, forecasting is not only possible, it's gotten remarkably good. And the story of how it got good is really the story of the second half of the 20th century and the first decades of the 21st. After the ENIAC forecasts of 1950, numerical weather prediction developed rapidly. The key was better computers, better observations, and better equations. Charney's filtered equations had been a brilliant workaround, But as computers grew more powerful through the 1950s and 1960s, meteorologists were able to go back to the full primitive equations, essentially the Navier-Stokes equations applied to the atmosphere, the same ones Richardson had tried to solve by hand. With faster machines, they could handle the sound waves and gravity waves that had plagued Richardson's attempt, not by filtering them out, but by using small enough time steps that those fast waves didn't blow up the calculation. The real breakthrough in operational forecasting came from an idea that's elegant in its simplicity, even though the mathematics behind it are fiendishly complex. It's called data assimilation, and it solves one of the fundamental problems of weather prediction. How do you figure out what the atmosphere is doing right now? You'd think this would be the easy part. Just look outside, right? But the atmosphere is three-dimensional. It extends from the surface up to the edge of space, and you need to know the temperature, pressure, humidity, and wind speed at every point in that entire volume. You have weather stations on the ground, but they're unevenly distributed, lots in Europe and North America, very few over the oceans, almost none over the poles. You have weather balloons, but they only go up twice a day from a few hundred locations worldwide. You have aircraft reports, ship observations, buoys, and then, starting in the 1960s, you have satellites. The first weather satellite, Tyros 1, launched on April 1st, 1960, and the images it sent back were a revelation. For the first time, meteorologists could see the atmosphere from above, the swirling patterns of clouds, the clear eyes of hurricanes, the vast comma-shaped signatures of mid-latitude cyclones. But satellite data is tricky. What a satellite actually measures is radiation, infrared and microwave energy coming up from the atmosphere and the surface. Converting that radiation into temperature and humidity at specific altitudes requires sophisticated mathematical inversion techniques. It's indirect, it's noisy, but it's global, and that changes everything. Data assimilation takes all of these observations, the surface stations, the balloons, the satellites, the aircraft, the buoys, and combines them with a short-range forecast from the computer model to produce the best possible estimate of the current state of the atmosphere. It's essentially a way of blending what the model thinks the atmosphere should be doing with what the observations say it's actually doing, weighting each source of information by how reliable it is. The mathematics behind modern data assimilation are based on optimal estimation theory and Bayesian statistics, and the algorithms, with names like 4D-VAR and the ensemble Kalman filter, are among the most computationally demanding calculations performed anywhere in science. Here's a number that might surprise you. The European Centre for Medium-Range Weather Forecasts, or ECMWF, based in Reading, England, is widely considered to run the best global weather model in the world. Their model divides the atmosphere into grid cells about 9 kilometers across and 137 layers deep, from the surface to about 80 kilometers up. Every 12 hours, they ingest something like 500 million observations from around the world and blend them into their model to create an analysis, a snapshot of the global atmosphere at that moment. Then they run the model forward, solving those primitive equations at every grid point, stepping forward in time increments of a few minutes to produce forecasts out to about 15 days. And the forecasts are good. Strikingly good, actually. A 5-day forecast today is about as accurate as a 1-day forecast was in 1980. That's a remarkable achievement. It means that over the course of about 40 years, forecasters gained 4 extra days of useful prediction. That might not sound like much, but think about what it means in practice. 4 extra days of warning before a hurricane makes landfall. 4 extra days for farmers to prepare for a frost, 4 extra days for cities to get ready for a blizzard. The economic value of improved weather forecasting has been estimated at billions of dollars per year, and the lives saved are beyond counting. But Lorenz's limit is still there, lurking. You can push the horizon outward with better observations and better models, but you can't eliminate it. And this is where one of the cleverest ideas in modern meteorology comes in. An idea that takes Lorenz's discovery and turns it from a limitation into a tool. It's called ensemble forecasting, and the concept is beautifully simple. Instead of running one forecast with your best estimate of the current conditions, you run dozens of forecasts, each one starting from slightly different initial conditions. You perturb the starting state, nudge the temperatures and winds and pressures by tiny amounts within the range of observational uncertainty. And then you watch what happens. If all the ensemble members agree, you can be confident in the forecast. If they diverge wildly, you know the atmosphere is in a sensitive state and the forecast is uncertain. This is exactly what Lorenz's work predicts. Sometimes the atmosphere is in a relatively stable configuration, and small errors in the initial conditions don't grow very fast. Those are the days when the 7-day forecast turns out to be spot on. Other times, the atmosphere is balanced on a knife edge, and tiny differences in the starting point lead to completely different outcomes. Those are the days when the forecast busts, when the storm that was supposed to track east goes north instead. Ensemble forecasting doesn't just tell you what the weather will probably do. It tells you how confident you should be in that prediction. And that's arguably just as valuable. The person who really championed ensemble forecasting at the operational level was a meteorologist named Eugenia Calnet, who led the Environmental Modeling Center at the U.S. National Weather Service in the early 1990s. Under her direction, the NWS began running ensemble forecasts operationally in 1992, and ECMWF followed shortly after. Today, every major forecasting center in the world runs ensembles. The ECMWF ensemble has 51 members, 50 perturbed runs plus 1 control, and the spread of those members is one of the most important tools forecasters use to assess confidence. And this brings us to something that connects all the way back to where we started, to the fundamental nature of what weather is. Remember how we talked about the atmosphere as a system driven by energy imbalances, the sun heating the equator more than the poles, the land warming faster than the ocean, the whole spinning, tilting, unevenly heated mess that creates pressure gradients and winds and storms. All of that physics is encoded in the equations that weather models solve. Every forecast is, at its core, an attempt to trace the consequences of differential heating through a fluid on a rotating sphere. The same physics that Hadley puzzled over in the 18th century, that Coriolis formalized in the 19th, that Richardson tried to compute by hand in the 20th. It's all still there, running on supercomputers that perform quadrillions of calculations per second. But there's another dimension to weather prediction that we haven't really talked about yet, and it's one that's becoming increasingly important as we push up against Lorenz's predictability limit. It involves a question that might seem paradoxical at first. Can you predict the weather beyond 2 weeks? The answer, surprisingly, is yes, but only if you change what you mean by prediction. You can't tell someone whether it will rain in their city on a specific day 3 months from now, but you can sometimes say whether the next 3 months will be wetter or drier than average, warmer or cooler than average. This is the realm of seasonal forecasting, and it depends on something fundamentally different from day-to-day weather prediction. It depends on the slow, ponderous variations of the ocean and in particular, on a phenomenon that reshapes weather patterns across half the planet: El Niño. You've probably heard the name. It shows up in the news every few years, usually when something dramatic is happening. Floods in California, droughts in Australia, coral bleaching in the Pacific, crop failures in East Africa. But the story of how we came to understand El Niño is itself a fascinating journey, and it reveals something deep about the way Earth's atmosphere and ocean talk to each other. The name itself is old. Peruvian fishermen along the coast of South America noticed centuries ago that some years around Christmas time, the normally cold, nutrient-rich waters off their shore would turn warm. The fish would vanish. The anchovies and sardines that thrived in the cold, upwelling current would disappear, and with them the seabirds, and with the seabirds the guano industry that was, for a time, one of Peru's major exports. They called this warm current El Niño, the Christ child, because it tended to arrive near Christmas. And for a long time, that's all it was: a local fishing problem, a warm current that showed up some years and ruined the catch. But here's the thing. What the fishermen were noticing off the coast of Peru was just one small piece of something enormous, something that spans the entire tropical Pacific Ocean and reaches its fingers into weather patterns on every continent. Understanding that took decades, and it started with a man who wasn't even studying the ocean. He was studying the monsoon. Sir Gilbert Walker was a British mathematician who arrived in India in 1904 to take charge of the India Meteorological Department. He'd been sent there in the aftermath of a devastating famine in 1899 and 1900, caused by a catastrophic failure of the monsoon rains. The British colonial administration wanted someone who could predict the monsoon, and Walker, a brilliant statistician from Cambridge, seemed like the right man for the job. He didn't have the tools we have now: no satellites, no computer models, barely any upper atmosphere observations. What he had was data. Decades of surface observations from weather stations around the world, and he had a gift for finding patterns in numbers. Walker did something that was, for his time, remarkably modern. He gathered data from dozens of stations across the tropics and started looking for correlations, what we'd now call teleconnections. He wanted to know, when the monsoon fails in India, is anything else happening somewhere else in the world that might have given us a warning? And what he found was striking. There was a seesaw. When atmospheric pressure was high over the western Pacific, around Darwin, Australia, it tended to be low over the eastern Pacific, around Tahiti, and vice versa. When pressure was high in the east and low in the west, the monsoon tended to be strong. When the pattern reversed, the monsoon weakened or failed. Walker called this the Southern Oscillation. He published paper after paper about it through the 1920s and 1930s, meticulously documenting the correlations. He showed that the Southern Oscillation was connected not just to the Indian monsoon, but to rainfall in Australia, temperatures in Western Canada, even pressure patterns in the South Atlantic. It was as if the entire tropical atmosphere was breathing in and out, and this oscillation was its rhythm. But here's the frustrating part. Walker could describe the pattern, but he couldn't explain it. He didn't know what caused the seesaw, and he couldn't predict when it would flip. His colleagues were skeptical. Some dismissed his statistical correlations as numerology, finding patterns in noise. Walker retired in 1934, somewhat discouraged, and the Southern Oscillation faded from mainstream meteorological attention for nearly 3 decades. It wasn't until the 1960s that someone put the pieces together. Jacob Bjerknes. And yes, that's the same Bjerknes family we'd encounter if we talked about the Bergen School of Meteorology. Jacob was the son of Wilhelm Bjerknes, who pioneered the idea of weather prediction as a physics problem. Jacob had emigrated to the United States during World War II and ended up at UCLA. In 1966 and 1969, he published landmark papers that connected Walker's atmospheric southern oscillation with the oceanic El Niño that Peruvian fishermen had known about for centuries. They were the same phenomenon, seen from two different angles. Here's how it works, and this is really beautiful when you see it as a coupled system. Normally, the trade winds blow from east to west across the tropical Pacific. Think about that for a second. Steady winds pushing surface water westward across the largest ocean on Earth. That piles up warm water in the western Pacific, near Indonesia and Australia, where sea surface temperatures can reach 29 or 30 degrees Celsius. Meanwhile, along the coast of South America, the surface water that's been pushed away gets replaced by cold water welling up from the deep ocean. That cold upwelling brings nutrients to the surface, which feeds the plankton, which feeds the fish, which feeds the birds. It's an entire ecosystem built on wind pushing water sideways. Now, above that warm pool in the western Pacific, the air is heated and moistened by the warm ocean below. It rises, forms massive convective thunderstorm complexes, and dumps enormous amounts of rain on Indonesia, the Philippines, northern Australia. That rising air has to go somewhere, so it flows eastward at high altitude, then sinks over the cooler eastern Pacific, where the skies are clear and the Atacama Desert, one of the driest places on Earth, bakes under perpetual sunshine. That sinking air feeds back into the trade winds at the surface, completing a giant atmospheric circulation loop. Bjerknes called it the Walker circulation, honoring the man who first detected its oscillation. So you have this elegant feedback loop. The trade winds push warm water west, which heats the air above it, which rises, which drives the circulation that maintains the trade winds. It's self-reinforcing. But, and this is where it gets interesting, it's also self-reinforcing in the other direction. If something weakens the trade winds, even slightly, some of that warm water sloshes back eastward. The eastern Pacific warms up a bit. That shifts some of the atmospheric convection eastward too, which weakens the trade winds further, which lets more warm water slosh east, which warms the eastern Pacific more. It's a positive feedback loop, and once it gets going, it can flip the entire system into its opposite state within a few months. That's El Niño. The trade winds weaken or even reverse. The warm pool spreads across the central and eastern Pacific. The rain follows the warm water, so suddenly you get torrential rainfall over the normally dry eastern Pacific, while Indonesia and Australia bake in drought. The cold upwelling off Peru shuts down, the fish disappear, and weather patterns across the entire globe shift because the location of that massive tropical heat source has moved thousands of kilometers. And the opposite phase, La Niña, is the system overshooting in the other direction. Trade winds stronger than normal, the warm pool pushed even further west, the eastern Pacific colder than usual. The Walker circulation intensified. The whole thing oscillates back and forth on a timescale of roughly 2 to 7 years, though it's irregular, which is part of what makes it so hard to predict. Now, here's why this matters for seasonal forecasting and why it lets us peak beyond Lorenz's 2-week chaos limit. The ocean is massive, it's slow, it has enormous thermal inertia. It takes months for those sea surface temperature anomalies to build up or dissipate. And because the atmosphere responds to where the warm water is, knowing the state of the tropical Pacific Ocean in, say, January, gives you real usable information about what the atmosphere is likely to do in March, April, May. You can't say it'll rain on April 15th in Kansas City, but you can say that during an El Niño winter, the southern United States tends to be wetter and cooler than average, and the northern tier tends to be warmer and drier. Those are statistical shifts in the odds, not deterministic forecasts, but they're real and they're useful. The first successful El Niño prediction came in the mid-1980s. Mark Kane and Stephen Zebiak at Columbia University's Lamont Doherty Earth Observatory built a simplified coupled ocean atmosphere model of the tropical Pacific and used it to predict the 1986 to 87 El Niño about a year in advance. That was a landmark moment. It showed that the slow ocean dynamics could be captured well enough to provide genuine predictive skill on seasonal timescales. Since then, seasonal forecasting has become a routine part of operational meteorology. Agencies like the Climate Prediction Center in the United States, ECMWF in Europe, and the Australian Bureau of Meteorology issue regular El Niño outlooks that inform agriculture, water management, disaster preparedness, and commodity markets around the world. And it's not just El Niño. Once you start looking at the ocean as a source of predictability, other patterns emerge. The Indian Ocean Dipole, which affects rainfall across East Africa, India, and Australia. The Atlantic Multidecadal Oscillation, which modulates hurricane activity in the North Atlantic over cycles of 60 to 80 years. The Pacific Decadal Oscillation, a longer timescale cousin of El Niño that shifts the background state of the North Pacific and influences climate across North America. All of these are examples of the ocean's slow memory, providing a foundation on which the atmosphere's chaotic weather dances. Think about what that means. Lawrence showed us that the atmosphere, left to itself, loses predictability in about 2 weeks. But the atmosphere isn't left to itself. It's coupled to an ocean that remembers. It's heated by a sun whose output we can predict with extraordinary precision. It's influenced by ice sheets and snow cover and soil moisture and vegetation, all of which change slowly enough to provide some anchor for forecasts beyond the chaos limit. The atmosphere is a fast, forgetful system riding on top of slow, patient ones, and by understanding those slow systems, we can extract surprising amounts of information about what the fast system will do on average. This brings us to something that's been quietly building throughout everything we've talked about tonight: the question of climate and how it relates to weather. Because climate, in a sense, is the ultimate slow system. It's the statistical summary of weather over decades, and it's shaped by factors that operate on timescales far longer than any individual storm or even any individual El Niño cycle. And right now, in our lifetime, something is happening to Earth's climate system that connects directly to every piece of physics we've discussed. The radiation balance, the greenhouse effect, the energy budget of the atmosphere, the circulation patterns that distribute heat from equator to pole. It's the story of how a gradual change in the composition of the atmosphere is altering the planet's energy budget in a way that has no precedent in the span of human civilization. And here's the thing. The science behind it isn't new. It isn't some recent invention cooked up by modern climate modelers. It goes back to the early 19th century, to a time when people were still arguing about whether glaciers had once covered Europe. In 1824, a French mathematician named Joseph Fourier, the same Fourier whose work on heat conduction gave us the Fourier transform, one of the most important mathematical tools in all of physics, published a remarkable paper in which he asked a seemingly simple question: why is the Earth as warm as it is? He knew how far the Earth sits from the sun. He could estimate how much solar energy reaches the surface. And when he did the calculation, he found something puzzling. If the Earth were just a bare rock absorbing sunlight and radiating heat back to space according to the known laws of radiation, it should be significantly colder than it actually is. Something was trapping extra warmth. Fourier suggested that the atmosphere itself was acting like a kind of blanket, transparent to incoming sunlight, but partially opaque to the heat radiating back out from the surface. He didn't have the details right, and he used an analogy to a glass-covered box that's been slightly misinterpreted over the years. But the core insight was sound. The atmosphere lets energy in more easily than it lets energy out, and that asymmetry warms the surface. Now, Fourier identified the effect, but he couldn't say which part of the atmosphere was responsible. That piece of the puzzle came from an Irish scientist named John Tyndall, working in the late 1850s at the Royal Institution in London. Tyndall built an ingenious apparatus, essentially a long tube that he could fill with different gases, with a heat source at one end and a sensitive detector at the other. He wanted to measure which gases absorbed infrared radiation, the invisible heat radiation that the Earth's surface emits, and what he found was striking. The main components of the atmosphere, nitrogen and oxygen, which together make up about 99% of the air, were essentially transparent to infrared. They barely absorbed any heat radiation at all. But trace gases, water vapor, carbon dioxide, methane, even in tiny concentrations, absorbed infrared radiation powerfully. Water vapor was the strongest absorber, and carbon dioxide was also remarkably effective. Tyndall immediately understood the implication. These trace gases, despite being a tiny fraction of the atmosphere, were the ones responsible for Fourier's warming effect. Remove them, Tyndall wrote, and the Earth's surface temperature would plummet. The warmth of the planet depended on gases that made up less than 1% of the air. Think about that for a second. 99% of the atmosphere is basically invisible to heat radiation. The entire greenhouse effect, the reason Earth isn't a frozen ball averaging something like -18 degrees Celsius instead of the comfortable +15 we actually enjoy, is maintained by trace gases. That 33-degree difference between a frozen Earth and a habitable one is held in place by water vapor, carbon dioxide, and a handful of other molecules that together amount to a tiny sliver of the atmosphere. It's one of those facts that sounds almost too precarious to be true, but Tyndall's measurements confirmed it, and every measurement since has reinforced it. The next leap came from a Swedish chemist named Svante Arrhenius. In 1896, Arrhenius sat down and did something extraordinarily tedious. He wanted to calculate, by hand, what would happen to Earth's temperature if the concentration of carbon dioxide in the atmosphere changed. He used data on infrared absorption that had been painstakingly measured by an American astronomer named Samuel Langley, who'd been studying how the moon's heat radiation was absorbed by Earth's atmosphere. Arrhenius divided the Earth's surface into latitude bands, accounted for the varying angle of sunlight, incorporated the effects of water vapor feedback, because warmer air holds more water vapor, which itself is a greenhouse gas, amplifying the initial warming, and after months of calculations, tens of thousands of individual computations done with pencil and paper, he arrived at an estimate. If you doubled the concentration of carbon dioxide in the atmosphere, he calculated, global average temperature would rise by about 5 to 6 degrees Celsius. That number, remarkably, is within the range of modern estimates, which place the climate sensitivity to a doubling of CO2 somewhere between about 2.5 and 4.5 degrees, with some possibility of higher values. Arrhenius was in the right ballpark with nothing but Langley's data and his own patience. Now, Arrhenius wasn't alarmed by this. He was actually motivated by the ice ages. He wanted to explain what had caused the great glaciations, and he thought fluctuations in CO2 might be the answer. And when he considered the possibility that industrial burning of coal might increase atmospheric CO2, he thought it might be mildly beneficial, making Sweden's winters a bit more pleasant. He had no way of knowing how rapidly fossil fuel combustion would accelerate over the 20th century. For decades after Arrhenius, the greenhouse effect was considered an interesting but not terribly urgent scientific curiosity. Many scientists assumed the oceans would simply absorb any excess CO2 that humans emitted, keeping atmospheric concentrations stable. Others thought the absorption bands of CO2 were already saturated, meaning the atmosphere was already absorbing all the infrared radiation it could at those wavelengths, so adding more CO2 wouldn't make a difference. Both of these assumptions turned out to be wrong, but it took careful work to show why. The saturation argument was dismantled in the 1950s by a physicist named Gilbert Plass, who used early computers to calculate infrared absorption at many different altitudes and wavelengths with far more precision than Arrhenius could manage. Plass showed that the absorption wasn't truly saturated. Adding more CO2 shifted the effective altitude from which the Earth radiated heat to space higher into the atmosphere, where the air is colder, which meant it radiated less efficiently, which meant more heat was retained. It's a subtle but crucial point. The greenhouse effect doesn't work by blocking radiation from the surface like a lid on a pot. It works by raising the effective radiating altitude, and since temperature decreases with altitude in the troposphere, remember the lapse rate we talked about earlier. A higher radiating altitude means a colder radiating temperature, which means less energy escaping to space, which means the system warms until a new balance is reached. And then there was the question of whether CO2 was actually accumulating in the atmosphere at all. That question was answered definitively by one of the most important measurement programs in the history of science, begun by a quiet, meticulous chemist named Charles David Keeling. In 1958, Keeling set up instruments at the Mauna Loa Observatory in Hawaii, high on a volcanic slope far from local pollution sources, and began measuring the concentration of CO2 in the atmosphere with extraordinary precision. What he found became one of the most iconic datasets in all of science, the Keeling curve. It showed two things. First, there was a beautiful seasonal oscillation, a sawtooth wave rising and falling each year as the northern hemisphere's vast forests and grasslands drew down CO2 in spring and summer through photosynthesis and released it in autumn and winter as plants decayed. The planet breathing, Keeling called it. And second, superimposed on that seasonal breathing, there was a relentless upward trend. Year after year, the baseline concentration of CO2 was climbing. When Keeling started measuring in 1958, the concentration was about 315 parts per million. Today, it's over 420. The oceans were absorbing some of the excess, yes, about a quarter of it, in fact. But they couldn't keep up. CO2 was accumulating in the atmosphere exactly as the physics predicted it would. So here you have the complete chain of reasoning, and every link in it was established by real measurements and real physics, most of it well before climate change became a political topic. Fourier identified the greenhouse effect in the 1820s. Tyndall identified the responsible gases in the 1850s. Arrhenius calculated the sensitivity to CO2 changes in the 1890s. Plass resolved the saturation question in the 1950s. Keeling proved accumulation was happening starting in 1958. each step built on the last. Each was tested, challenged, and confirmed. And the modern climate models that project future warming? They're direct descendants of the same numerical weather prediction models we talked about earlier. Richardson's dream, Charney's filtered equations, the grid-based computations that von Neumann's computer first made possible. Climate models are essentially weather models run for centuries instead of days, coupled to ocean models, ice sheet models, land surface models, and atmospheric chemistry models. They solve the same Navier-Stokes equations, the same thermodynamic equations, the same radiative transfer equations. They're more complex, of course, because they have to represent slow processes, ocean circulation, carbon cycling, ice dynamics, that weather models can ignore. But the physics is the same physics. When a climate model projects that doubling CO2 will warm the planet by about 3 degrees Celsius, it's using the same radiation physics that Tyndall measured, the same fluid dynamics that Bjerknes formulated, the same numerical methods that Charney pioneered. The entire intellectual heritage of weather science feeds directly into our understanding of climate change. And here's something worth sitting with. The atmosphere doesn't know the difference between weather and climate. There's no switch that flips. Climate is just weather averaged over time, shaped by the boundary conditions. How much greenhouse gas is in the air, how much ice covers the poles, how the ocean currents are configured. Change those boundary conditions slowly, and you change the statistics of weather. You shift the distribution. The average moves, but so do the extremes. A world that's 2 or 3 degrees warmer on average doesn't just feel slightly warmer on a typical Tuesday. It means heat waves that would have been extraordinarily rare become common. It means the atmosphere holds more water vapor, about 7% more for every degree Celsius of warming, following the Clausius-Clapeyron relation, which means when it does rain, it rains harder. It means the energy available to fuel tropical cyclones increases. It means ice melts, sea levels rise, ecosystems shift. The physics connects all of it. But I don't want to leave you with anxiety tonight. I want to leave you with something else. A sense of how remarkable it is that we understand any of this at all. Think about the arc of what we've covered. We started with ancient Babylonians watching the sky and trying to read omens in the clouds. We followed Aristotle's first attempt to reason about the atmosphere, flawed but brave. We watched Torricelli discover that we live at the bottom of an ocean of air, and Pascal prove it by sending his brother-in-law up a mountain. We saw Hadley puzzle out the trade winds, and Coriolis explain why storms spin. We followed the Bergen School as they invented the concept of weather fronts in the aftermath of a world war, and Richardson as he dreamed of a forecast factory staffed by thousands of human computers. We watched that dream come true when von Neumann and Charney coaxed the first numerical forecast from ENIAC. We stood with Lorenz as he discovered chaos and realized that perfect prediction would always elude us. We followed satellites into orbit and watched them transform our view of the planet. We traced the ocean's slow memory through Walker's southern oscillation and Bjerknes's elegant coupling of atmosphere and sea. Every one of those steps was taken by a real person, often working against skepticism, sometimes in obscurity, occasionally in tragedy. Fitzroy, who gave us storm warnings and took his own life. Richardson, whose forecast failed spectacularly, but whose method was ultimately vindicated. Walker, who retired thinking his life's work on the Southern Oscillation had been a dead end, never knowing that Bjerknes would complete the picture decades later. Arrhenius, who calculated the greenhouse sensitivity by hand over months of tedious work, never imagining how urgent his result would become. What connects all of them is curiosity, a desire to understand why the wind blows, why the rain falls, why the temperature drops before a storm. The atmosphere is the most complex fluid system most of us will ever encounter, and the fact that we can predict its behavior days in advance, understand its patterns seasons ahead, and project its long-term trajectory decades into the future. That's one of the great intellectual achievements of our species. It took centuries. It took thousands of people. It took barometers and telegraphs and satellites and supercomputers. It took brilliant mathematics and patient observation and, honestly, a fair amount of failure. And it's still going. Right now, tonight, as you're lying here, weather models are running on supercomputers in Reading, England, and College Park, Maryland, and Tokyo, and Melbourne, ingesting millions of observations, solving billions of equations, producing forecasts that will help farmers plant crops, and pilots avoid turbulence, and emergency managers prepare for storms. Satellites are circling overhead, measuring sea surface temperatures and cloud heights and wind speeds and atmospheric moisture with instruments that would have seemed like pure magic to Torricelli or Hadley or even Richardson. Somewhere, a graduate student is staring at a dataset, noticing a pattern no one has seen before, and wondering what it means. The atmosphere is still out there doing what it's always done, absorbing sunlight, radiating heat, moving energy from where there's too much to where there's too little, spinning up storms and calming them down, carrying water from the oceans to the continents, and back again. It doesn't care that we understand it a little better now than we used to. It just keeps going. But we understand it. Imperfectly, incompletely, but genuinely. And that understanding, built up over centuries by people who looked at the sky and refused to stop asking why, is one of the most beautiful things we've ever done. So let that settle over you. Let the wind outside, if there is any, be a reminder that the atmosphere is always at work, always in motion, always following the physics. And let yourself drift off, knowing that the same curiosity that drove Torricelli and Hadley and Lorenz and all the rest is still alive, still asking questions, still reaching for answers. The sky will be there in the morning. For now, just rest.